this amazing seminar, web seminar. So I will share my presentation right now like this. So let me put it in full. There it is. So hello everyone. This is a kind of overview of the work done in topological dynamical properties in the context of Turing machines in the last few years. So let's start. First, let me put some context to this work. This is what we think when we hear the word Turing machines. It has a set of states that is represented in this graph by the circles. A set of alphabet, that is what it recognizes in the input. A special initial state that is marked by this empty arrow here. A set of final state that in the graph is represented by a double circle. A special symbol called blank symbol that an infinite grid of one dimension is full of them, but in the center part where it is the input presented. And finally, a transition function that is represented by the complete graph here. And for example, here, if we have the full grid, a one-dimensional grid, with a special element that is the head that is pointing to one cell in particular, and it works in the following way. If we have, in this case, a state right arrow, if we see the symbol 1 here in the tape, we replace by 1 following this instruction, and goes to the left, to the state left arrow. Now in this case, with the state left arrow, if we see the symbol 0, we replace it by symbol 1 and go to the right to, again, the right arrow. We are not interested in some of the details of the general Turing machines when we studied like a dynamical system. In particular, we are not interested in initial or final states because we're not want to start at some special point or halt at some special point. We are also not interested in particular special symbols because we want to know the whole dynamics that is possible to have. So we work even when we have tapes that are not homogeneous. Also, we are not interested in partial function. We are interested in what is called complete Turing machines that have every possible combination between the internal state and read symbol to following the computation indefinitely. Also, we have problems with this kind of configuration when we are pointing to a particular cell in the grid because we could have a problem with compacity. So it is considered two possible solutions. The left one is called the Turing machine with moving tape that is center the state at the 0 position and move the tape accordingly. And this right proposition, that is Turing machine with moving head, that the solution is incorporate the state inside the tape as a new symbol. Both type of system evolves with the instruction in the following manner, following the instruction, but in the case of TMT, is the tape that it moves instead of the head, and in TMH configuration is the cell that has the actual state that it moves to the left or right, like this. So we can also consider what is called the trace shift, that is the column factor of TMT, is that we consider the central part of the computation, the whole history of the computation, taking the pointed symbol and the internal state of every configuration, and we consider a infinite word that it captures all the history of the central part of the whole computation of the machine, and this evolves through the shift function, making a subshift like this. Both TMH and TMT were proposed by Kůrka in his seminal paper in 1997, and is done because Kůrka wants to define correctly topological system for Turing machines, and not having capacity is a serious drawback citing his words. Both systems can be endowed with the Cantor metric, so both are compact and are perfect system. Perfect system means that it has no isolated points. The column factor of TMH can be considered, and also we can consider column factors with more than one symbols, but they are not of interest in this particular talk. Also, if we consider the transformation from normal topological Turing machines to TMT, we are losing the information of the position of the tape. And if we transform to TMH, we are not losing any information, but we cannot achieve what is called the headless configuration, that is configuration with no position with an state. And those are the fixed point of TMH. If we go forward in time, we read a symbol, change it, and moves to a direction or left or right. But if we are backward in time, we need to first move and then change the symbol, and that is not what a typical Turing machine is. So it's a problem to define Turing machines in the opposite time direction. Normally, it is done by just consider movement or writing instruction, but that is not possible when we consider dynamics, because we are modifying the dynamics, in particular, cutting in half the speed of the Turing machine if we don't do that. So what is our proposal, or the normal way that is resolved, is that as every state of a reversible Turing machine can just be attainable from one particular direction, we consider that direction to be mu of this state. And if the regular Turing machine is defined by this kind of instruction, considering that mu of the attainable state, then the reverse instruction consider is what we write is what we read, but we move in the opposite direction of the attained state. If we do that, if we compose the Turing machine with this new reverse machine, what we get is the homomorphism that is just the same tape, but with the position of the head shifted to the left or to the right, depending on the state when we are. Other way to get the reverse is to consider the Turing machine, transform it to just writing or movement instruction, reverse this instruction, and then redo the movement writing instruction with the new information, and we get the same result that the previous method. The opening result of Kůrka 1997 are related that if for any Turing machine, we always get a configuration that its evolution goes indefinitely to the right, or work in the right part of the table instead, sorry, and never gets to position -1 or relative position -1 if we are talking about the Turing machine moving table. So that roughly implies some interesting initial results. The first one is that nor TMH, neither DMT can be positively expansive. So if what it is that if we have two different configurations that the difference is in the left part of the tape, they cannot differentiate in the time, never, because the whole evolution is done in the right part. The same happens when bijective TMH, but with expansivity. This means that the difference is not seen in the future nor in the past. And TMH nor TMT can have one attractive periodic point. If we have that we cannot modify the left part of the tape, we at least have two attractive periodic points by any Turing machine, so it's impossible. Also, more interesting results are that TMH has zero topological entropy, and also was conjectured that TMT cannot be aperiodic, or every TMT has a periodic point, or what if we use the same word that was used in the first talk of this session. Every Turing machine has at least one weekly periodic point. These both results are very interesting, and it initiates a very rich field of research. The first one that I want to address is the entropy route. So, first of all, we need some interesting technique to understand some of the result of this part. This technique is called reversing the time, and what is that if we have a Turing machine that is reversible and incomplete in this case, we can attach the reverse Turing machine through the homeomorphism phi, such that this machine gets a property called innocuous. Being innocuous is that if we start, for example, at the state R1 plus, if the computation eventually halts, it halts at a state R1 minus and with the same state content. So the machine does nothing if it halts. So we center this part in topological entropy in TMT. The topological entropy in TMT is defined by this trace, and what is a limit over the variety of the language of certain size divided by this size in the trace. Early work of Blondel et al. In 2004 shows that this property is undesirable for TMT, but consider multiple tapes model. So with just one tape, that is the model that we work, it is possible to calculate the entropy with any any possible error greater than 0. This result is from Jandel in 2014, and Rowley used a result from Brutno that the entropy is possible to calculate through Kolmogorov complexity. I know the Kolmogorov complexity is not possible to decide either, but it is proven also that the entropy is reached at maximum in the set of configuration C+. The set of configuration C+ is the set of configuration that never gets position -1 or relative position -1. And the evolution of this kind of configuration always touch every bisected cell a finite amount of time. Then the evolution goes indefinitely to the right, never returning. So with this kind of configuration, it's possible to construct a finite automaton. And this finite automaton has, thanks to the previous configuration that is passed, the diamond property that given two vertices, in this case, are the states, and one word U, that in this case are the word of the alphabet, we can get from A to B with word U at most in one possible path. With that, Bruno showed that it's possible to calculate the complexity in this kind of finite automaton, and then it is possible to approximate the entropy of TMT from above. But if we are trying to approximate from above, it is possible to decide if the entropy is actually 0. And the result is no, it's not possible. This result from Gajardo, Olanger, and myself is that it's not possible indeed calculate the entropy of 0. What this does is that we consider a very simple simulation of a two-counter machine that is reversible, C, such that we consider the counters to be an amount of 1 with borders, special borders, in this case, the greater, less than, and stick symbols. And we want to work over a tape full of ones if the space is available. So 4 types of different configuration will be possible. The first one is that we don't have enough ones in the tape to move the borders of the configuration. We don't find the borders of the configuration, and we're trying to find it through searching through ones to the left or right. We have correct configuration and we have enough space to work. So we have successful infinite computation of C, or we have enough space and successful finite computation of C. So if the computation finished, it is allowed to start a new computation with NP counters looking to the right, and we start when we find a new stick symbol. Then we use the technique reversing the time, and what we get is that when the configuration has garbage, the machine goes forward in time, Alt, and start the reverse version and keeps looping in a static or strong periodic point. When we try to search from a symbol, a special symbol, and we don't find it, we get a weakly or shifted periodic point, seeing just one kind of symbol, that is the symbol 1, so it's not much variety in the language. We can have infinite computation of machine C, so we are having to return indefinitely to position 0, where is the left border of the configuration simulated. And therefore, the unique possible configuration that can have a positive entropy is if we start with 0 counters, counters with 0, sorry, and we have that matching C alts with counters in 0. If it is that, we give N1, N2, N3, etc., all greater than the enough space to work until we reach the final state of machine C, and then we simulate machine C, we finish the computation, and then we find the next stick symbol and we start again, and again and again. So if machine C alt, we can have this kind of configuration that has positive entropy. then it's undecidable. Now, the aperiodic root of this rich field of research. What is the idea to have possible aperiodic machines that don't have any static shifted weakly periodic points? We have one to the left and one to the right, and we are in the middle. And we work searching from the symbol of the right. We push the symbol of the right one position to the right, then we return to the one to the left and start again. In this case, we are increasing the amount of zero between the two ones, so we never make the same computation again. The problem is that if there not exists the symbol one to the left or the symbol one to the right, we will search this symbol indefinitely and we will enter in a weakly or shifted periodic point. So, what is the solution? A possible solution is what is called Hooper calls. What is a Hooper calls is that we make a sub-search in a bounded space, and in this bounded space we try to push in this case the one to the right, and when we get not enough space, we return this bounded call. But if we have enough space and we then again have not find the new one in the new space, we make another Hooper call. So let's do that in our simulation. Then here I want to find the one to the left, to the right, sorry. Then I mark a one to the left, a one to the right in this bounded space, and now work normally, try to push the one at the right. But I don't have the enough space to push that one. So I return the Hooper call and effectively advance just one space. Hooper calls was introduced by Hooper in 1966, not with that name, to prove the undecidability of mortal problem. The mortality problem is that if a Turing machine is indeed mortal, mortal is that if the machine holds in every possible configuration. This is considering also non-homogeneous configurations. So it's not the same that the totality problem. Mortality was further improved by Carey and Olanger in 2008, proving that this problem is also undecidable for reversible machines, and later by Zenil by characterizing what an immortal configuration is. The first example, therefore, of a Turing machine that indeed is aperiodic was by Blondel, Cassegne, and Nishito in 2002, and this particular machine that you see here is a compressed version of the original machine presented in that work that is, if I recall correctly, like 36 states. And as can be seen in the diagram, this machine is not reversible. In Carey-Olanger 2008, it was presented an incomplete but reversible aperiodic Turing machine, and it was also proved that the aperiodicity problem, but in reversible Turing machine, is undecidable. Also, it was conjectured the existence and undecidability of aperiodicity in complete and reversible Turing machine. So, before continuing, I want to present another and the last interesting technique that is called embedding. Embedding needs innocuous machines, the machine that does nothing. And when we have a complete machine that is called the host, and we have an instruction that goes from state R to state Q, we take out that instruction and connect the innocuous machine like this. As the innocuous machine in general does nothing, so the world dynamic of the host machine is preserved if we effectively compute finitely inside I, the machine that is innocuous. So, in 2017, by Ksenia Olanger and myself, was present what is called smart machine. Smart machine respond to the conjecture of 2008 by Kari Olanger that this is in fact a complete and reversible aperiodic Turing machine. It computes as the same idea of the Hooper calls, but not only to the right, but also to the left. The machine is symmetric in space and time. Its transitive is also a substitution, in fact, a primitive substitution, and is the first example of very interesting property. For example, it's the first machine to have topological transitivity in TMH. What is topological transitivity? If we have two finite configurations, that is finite words in the language of TMH, exists always a completion of this configuration, W and C, and a time n such that the evolution of the Turing machine at time n of this new configuration will contain the second finite configuration B. With the embedding technique, it is possible to prove the undecidability of topological transitivity using a reduction of the aperiodicity problem from reversible and incomplete Turing machine of Kari Olanger. The smart machine is also the first example of topological minimality in TMT. What topological minimality is that for every possible configuration X and every possible finite configuration B, a word in the language of TMT, always exists a time such that evolving X will contain configuration B. This is X, in this case, is called a transitive point, and we can define transitivity also with the transitive, and as our system are perfect, the both definition of transitivity are equivalent. For minimality, it is needed that we don't have any periodic points. So it is expected that after we find the first example of a periodic Turing machine, we find the first example of topological minimality. Of course, it is we need some more properties to have minimality. In fact, there exists aperiodic machines that are not minimal. In fact, you can just copy two copies of smart, and if they are not connected, it's impossible to have minimality, and the system is, in fact, aperiodic. Again, using embedding, it's possible to prove the undecidability of this property with a reduction, in this case, of the mortality problem for reversible machine, again from Kari Olanger 2008. If we consider the following property, is called blocking words. A blocking word is just a finite word or configuration that it doesn't matter what is the context of what is put in the context of this finite configuration, it never gets position -1. Blocking words is an undecidable property and is proven by a it's like the same idea that was used to prove the topological entropy zero undecidability. It's a more or less the same idea. With that, we can have this map. This map represents, not in size no, is the subsets, the whole world of transitive trace shift. So every possible intersection that you can see here have an infinite amount of Turing machine. In particular, here in the intersection between TMH transitivity and TMT minimality is smart machine. And we can have one example of every possible sub set in this map. As I said, every subset in the map has countable many Turing machines, and with embedding technique, it's proven to keep or erase some of these properties when we get the new machine. If we consider H the host machine, I the innocuous machine, and H sub I the formed new machine, then the reversibility is kept from H to HI and vice versa. If machine I is aperiodic, both in weakly or strongly, the aperiodicity is kept from H to HI. If I is aperiodic and we add a smaller alphabet, then the transitivity is kept from one to another H and HI. If machine I is mortal, the minimality is kept from machine H to HI and vice versa. And finally, if I is immortal, then HI can never be minimal. That implies that minimality and transitivity are separated in the sense that in the presence of transitivity, it cannot be decided the minimality. Another interesting topological property is topological mixing. Topological mixing is that if we have two finite configuration words in this case in TMT, and for every time bigger n that is greater than a border that in this case is called lower n, that lower n depends of the finite configuration U and B, it is always possible to have completions W and C such that the evolution of this finite configuration completed by W and C in the time n contains the word of finite configuration B. This property is harder, is more, it contains topological transitivity. It is possible by a combinatorial proof that to prove that the smart machine is topological mixing. That was unexpected when we get that result. Considering embedding also, it's possible to prove that every mixing notion is undecidable from Turing machine, doing a reduction of a periodicity problem inside the chief machine. Also, topological weak mixing, that is the square system is transitive, is decidable in every embedding of known minimal Turing machines. This talk was a non-exhaustive compilation of some of the work done inside the research of topological dynamical properties. The majority of the work that is adjacent to topological properties were not touched in this talk. And I want to address or highlight the interesting work of Pierre Guillon, Ville Salot, Ana Gajardo, and many, many other people that are done many and rich research in the adjacent of these topological properties. Please, apologies in advance for any people that I let outside of this talk. Two interesting results that I want to address is that Gajardo and its co-workers about the sensitivity, continuity, and sophisticity of topological Turing machines, And this result that was highlighted by the presentation of Tony, that said that aperiodic machines have a sublinear movement in the space with a first result by Jandel and later a tighter asymptotic behavior by Guillaume-Salon. There exists plenty of work left in this field of research. Example of question about that arise of this type, for example, if there exists a minimal but non-linearly recurrent Turing machine. What is that is that if in the trace, every possible word is found at most at a time that depends linearly of the size of the word. If such machine doesn't exist, we don't have any example of that, topological mixing will be, in fact, decidable in minimal Turing machines. Other interesting question has relation with the arithmetical hierarchy of some of the topological properties that are not classified tightly yet. And the previous result is highly connected to that. Finally, it will be decidable. It will be nice that we could have a rest-like theorem from topological properties, considering just one tape, because in the work of Blondel and others in 2004, it was proved that there exists a rest-like theorem, but for more than one tape model. So I want to thank to my fundings, Fondesit, ANIT, EcoSud, the University of Bio, and the laboratory Glypho. This was my presentation. I hope that you could enjoy it, and it was enough or enoughly clear. Thank you. So I don't know. I can answer question right now. Okay, so.